This video is a first in a series of 3 for Lesson 5, which is on complex numbers. This video will be on operations with complex numbers and the conjugate pairs theorem. The second video will be on using the conjugate pairs theorem to find the zeros of polynomial functions. The last video will be on a word problem. We have to know how to deal with imaginary numbers now. Up to this point, we haven't done much with them. But say, for example, you ended up with square root of negative 36. You had to simplify it, or you had to deal with it. How you deal with it is to factor out a -1. And these can be separated because they're multiplied together. You may or may not remember that the square root of -1 is represented by the letter I. And the square root of 36, we know, is 6. The square root of -36 is simplified down to 6i. This is a form that we can use. Let's look at another one. The square root of -27, in its current form, we cannot work with it. Again, we want to simplify, get the negative out from under the radical. Factor out the -1. Then you may remember on simplifying radicals, you want to factor the number into something that's a perfect square and another number. I can factor 27 into 9 times 3. I'll have square root of 1 times square root of 9 times square root of 3, or square root of -1. The square root of -1 is I, the square root of 9 is 3, and the square root of 3 stays under the radical. Square root of -27 simplifies down to 3i times the square root of 3. If you are adding complex numbers, think about combining like terms. 8 can combine with the 3. The complex numbers 6i and 2i can be combined. 8 plus 3 is 11. 6 plus 2 is 8i. Same thing with subtraction. Oops, forgot the minus. Almost forgot it again. As with any subtraction, you'd have to distribute the sign, that negative to your second set of parentheses. And then you can combine like terms. 4 minus 6 is -2. 5 plus 3 gives me 8i. Let's look at multiplying. I have 3i times 6i. We can multiply the real parts. 3 times 6 is 18. We can multiply the i's. Think of it like a variable. I times I will give me I squared. Now, if you put this in My Open Math, it would say you're partially right. Got to keep simplifying. And it has to do with that I squared. So I squared is the square root of negative 1 times the square root of negative 1. So basically what you've got is the square root of negative 1, the whole quantity squared. And we know that when you have your power that matches the index, they undo each other and you're left with just what is under the radical. So I squared is equal to negative 1. What we have here is 18 times negative 1. So my final simplified answer would be negative 18. Let's look at another example of multiplication. Actually, let's save that. Treat this just like any binomial times a binomial. You can use the FOIL method. 8 times 5 is 40. 8 times 4i is 32i. Negative I times 5 will be a minus 5i. Negative I times 4i will be negative 4i squared. Then it's a matter of combining like terms and doing any simplification like with that I squared. The i's, I want to combine those, and that will be 27i. And we have to remember that, let's see, I squared is the same as negative 1. So negative 1 times negative 4, that will become positive 4. And now I can combine these like terms. So this became this. Now let's look at the conjugate pairs theorem. A little bit of math jocularity. Get it? Good things come in pairs. I should have a laugh track. I gotta find a laugh track to go along with this. All right, here is our conjugate pairs theorem. If R, and we've used R before, like if I said if R is an x-intercept of a function, we can write the factor as x minus R. Using it the same way, if R equals a complex number, and I should say a complex number has a real part and it has a complex part. But this complex number is a zero of our function. If we know that, then we know that its complex conjugate, which is represented by R with a little bar over it, and here is its complex conjugate, is also a zero of f. They travel in pairs as complex conjugates. Let's take some of this off. So we know this is telling us this for sure is a zero of the function, and because of this conjugate pairs theorem, we will automatically know that the a minus bi will also be a zero of the function. So as it says here, complex zeros travel in conjugate pairs. You cannot have one without the other. One of the questions in the homework is like this. They will tell you the degree of the polynomial. They will tell you some of the zeros, and they want you to find the remaining zeros. Why do you suppose they tell us the degree? Why is it important that they tell us the degree of the function when they want us to find the remaining zeros? Now I could play the Jeopardy theme song. You might remember when we introduced polynomial functions that the degree of the polynomial function will tell you the maximum number of zeros. When they tell us the degree, we know we need to have a total of 5 zeros for this function. All right, so we know we've got 1, we've got I, and we've got 2I as zeros. We've got 3, that means we need to find 2, and we are going to make use of this conjugate pairs theorem to find those other 2. This is complex or imaginary, this is complex and imaginary. They will have a conjugate pair. Now remember, the conjugate pair, the sign changes with the imaginary part. If I is a 0, then negative I will also be a 0. Positive 2i is a 0, then negative 2i will also be a 0. Now I have a total of 5 zeros. I have found the remaining zeros of this function. I don't know, puppies are cute. They travel in pairs. I just had to throw that in. All right, now try this one. You've got a degree 6, and they're giving you a 0 of I, a 0 of 3 minus 2i, and a 0 of negative 2 plus I. You've got to find the 3 remaining zeros. So pause this, and then start it up when you're ready for the exciting answer. If I is a 0, then negative I will be a 0. 3 minus 2i. Remember, the sign changes with the complex part. The first number stays the same sign. 3 minus 2i goes with 3 plus 2i. The last one, the negative 2 plus I, will be negative 2 minus I. And there we have found the remaining 3 zeros for this function. So this concludes the first video. The next video will be on using that conjugate pairs theorem to either find the equation of the function or to find remaining zeros of a function.